One of the skills that we're going to need in at least this beginning part of chapter 8 is to complete the square. Now, why are we doing that? Because we're going to be asked to deal with equations of spheres. And one of the skills we need is to be able to complete the square. So I just wanted to do a quick refresher here. So when we complete the square, that doesn't actually mean that we're solving this equation. We're not trying to find x values. If we were trying to find x values, then we'd really have 3 options. Completing the square is one of those options. Using quadratic formula or hoping that it factors are other options. But if we have to complete the square, I'm going to go through this pretty quickly because hopefully it's something you've seen before. The way that I approach this is I'm going to focus in on the x parts. So that x squared plus 4x. And I'm kind of going to scoot that 7 off to the side for a minute. So I'll scoot my -7 off to the side. The idea with completing the square is that I'm looking to put some magic number in so that this part of it could be written as x plus or minus a number whole thing squared. And after we've done 100 of these, or because you remember from an algebra class once upon a time, there's kind of just a method to doing it. I look at the coefficient in front of the x term. I take half of that. So half of +4 would be +2. So I'd have x plus 2. In order to make this work, if we actually multiplied out x plus 2 squared, we'd have x squared plus 4x plus 4. But we didn't have a plus 4 in the original problem, so we just put it in. And then in order to not change the problem, we're going to subtract it back off. So when we talk about completing the square, that means we're aiming to write this whole thing as some sort of perfect square is equal to a number on this side. So I'm going to take that -4 and the -7, combine that to be a -11, and if I added that to both sides, that is what my result would look like. And this, I would say, is completing the square. Now, we could also write this, it would also be correct to write that as x plus 2 squared minus 11 equals 0. This is also correct. Now, the second part of my question is really where we're going with all of this. So if I had a circle and I had x minus 3 squared plus y plus 1 squared is equal to 16, and I asked you to find the center and the radius, then we would find the center from looking at what makes each of these perfect square pieces equal to 0. So for an x coordinate, if I plugged in 3, that would make this term equal to 0. And if I plugged in -1, that would make this term equal to 0. So that's where the center is, 3, -1. In terms of the radius, well, the radius is the square root of whatever number is hiding on this side. So the square root of 16 is 4, so my radius is 4. In math, we draw this coordinate system differently than it's usually drawn in physics. So I'm just pointing that out to everybody. We call it a right-hand coordinate system, and there are a couple of mathematically correct right-hand coordinate systems. This is the one that we choose to use in calculus. We make the x-axis coming out at us, the y-axis headed that way, and the z-axis pointed straight up. Then we can define a point in space, like in 3-dimensional space, based on an x, y, and z coordinate. So for example, if I was looking at the coordinate 2, 1, 4, just like with 2-dimensional coordinates, where we have a convention that says the first number is always the x and the second number is always the y, when we have our three-dimensional coordinate system, we end up with, dropping my pen, but we end up with X, Y, and then Z. This tells me that if I wanted to get to that coordinate, I would take 2 steps in the X direction, and then 1 step in the Y direction, and 4 steps in the Z direction. Now, if I had to actually sketch that on a graph, I'm not so good at graphing in 3D, but I know how to get all my points. So if I had to sketch that in 3D, I would draw out taking 2 steps in the X direction, and then taking 1 step over in the Y direction, and then taking my 1, 2, 3, 4 steps up in the Z direction, and then I would just label that point. That is a point 2, 1, 4. It's really not that important that you can sketch things in 3 dimensions in the context of 17B. We will do a little bit more with this in 17C. So it's good to just get a little bit of practice right now. In the context of 17B, things that we're going to have to sketch and answer questions about sort of include spheres in a 3-dimensional space and planes in a 3-dimensional space. Now, a plane is really just, we can think about a plane as a flat sheet. So a flat sheet of paper, that's a plane, not the kind of plane that you might get on and fly to Antarctica, but a flat sheet is what we're talking about with planes. So there are, I don't know how, has anyone started the web work homework? No, let me not ask that. I have looked at all of the web work homework. So today I'm going to focus on the things that I know we're going to need for the web work homework. So let's talk about spheres, and then let's move on to start talking about vectors. And we'll hold off on planes until Wednesday. So here's a point. It's floating out there in space. Good times. And one thing that maybe I would be asked to do, let's turn this into a few questions. So my first question is going to be to find the distance from this point to the origin. And then my second question is going to be to find the equation of the sphere with this point at the center and passing through the origin. Well, if we take a stab at this first part of the question, and I'm not going to work through all of the messy algebra, but I do want to just sort of give you a visual sense of where the messy algebra is coming from. So we have a distance formula for finding the distance between 2 points. So just kind of to refresh our memory, distance formula for between 2 points, I'd have like x2 minus x1 squared plus y2 minus y1 squared. And really, that's coming from Pythagorean theorem. Well, it turns out that when we do this in 3 dimensions, the distance formula is almost exactly the same. And that distance formula looks like the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And if you're someone who doesn't like to take every formula at face value, and you'd actually like to figure out where this is coming from, the algebra is a little bit messy, but I'm going to try to visualize this. So the distance from here to the origin is actually the hypotenuse of a right triangle. And to build that right triangle, we'd have to have a distance here, which is the hypotenuse of a different right triangle, and the distance here, and then we'd be finding the hypotenuse of that other thing. And if you work out the messy algebra, you'd get this equation. If you're willing to just take my word for it, then the way that this looks is the coordinates for the origin are always 0, 0, 0 if we're in 3 dimensions. So if I have to find the distance from this point to the origin, that's just telling us that the x1, y1, and z1 are all equal to 0. So this distance would turn into the square root of 2 squared plus 1 squared plus 4 squared. Or let's see if I can do math today. 4 squared, that's 16, plus another 4, that's 20, plus a 1, so square root of 21. Now the second part, to find the equation of a sphere with this point as the center and passing through the origin, well, in 2 dimensions, our equation for a circle looks like, I usually write it as x minus x naught squared plus y minus y naught squared is equal to the radius squared. And to go from a circle to a sphere, we just scale that up by changing this around to look like x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to the radius squared. So if this point is going to be at the center, I can erase that x naught, y naught, z naught, and replace those by the coordinates at the center, the 2, 1, and 4. And conveniently, if this sphere is going to touch the origin, then I know that this distance right here is the radius. And we just found what that distance was. We found that that radius was the square root of 21 in part A, which means that I can replace that r with the square root of 21 and make the whole thing squared. Bam, we got the equation of a sphere. Could you simplify that? Absolutely. Do I need to? Probably not. There are a lot of different notations that we use for vectors and kind of different ways to conceive of vectors. But at its heart, a vector is something with a length or magnitude and a direction. Now, usually in math, when we're thinking about vectors, we're thinking about drawing a vector in space with what we call a head and a tail. So a vector really just looks like an arrow, and we call this side the head, and we call this side the tail. This same vector, which if we think about in the context of having a length or a magnitude and a direction, well, this vector, I can see the dots on my board. I don't know if you can see the dots on my board. This vector is really the hypotenuse of a triangle that's 2 on this side and 1, 2, 3, 4 on this side. So one way that we can think about this vector is saying it goes 2 to the right and up 4. Now I've used square brackets to define this as a vector. This is not the notation you're going to see on the web work. What you're going to see on the web work is square brackets, but you're going to see this listed vertically as a 2 and a 4. I prefer this notation because then I know we're not talking about the coordinate 2, 4. We're talking about a vector that points 2 to the right and up 4. Because mathematically, if I had a giant coordinate system here, this vector, and I'll give it a name. I'm going to give it the name A, and I'm going to put a hat on top of it, or sorry, I'm going to put a little vector on top of it to denote that it's a vector. That vector that points 2 to the right and up 4, well, it's the same vector if it's sitting over there, or sitting over here, or sitting up here, as long as it has the same length and direction, it's the same vector. That's not super important in math, but it is important in physics. So it does come up sometimes that we really need to make sure that we're not always just drawing the vector with its tail at the origin. I can pick this vector up and move it anywhere as long as I haven't changed the length or the direction. So back to other notations that we might see. There are some problems in the textbook that give even a different notation for this vector. By the way, I'm going to write this as a equals. This notation is definitely what Professor Choduri was using in class with putting a vector hat on top. And that's my preference. In our textbook, they actually just make the letter bold. And sometimes that's how it is in the web work as well. But I don't know how to write bold on the board, right? On a keyboard, it's fine. I can hit Control B, I can make it bold. But on the board, I can't do that. The other notation that we do sometimes see would be to write this as 2i plus 4j. This notation is pretty common in physics, and the I and j there are just telling you I corresponds to taking one step in the x direction. J corresponds to taking 4 steps in the y direction. So that's kind of how I think about this notation, is it's how many steps in the x direction plus how many steps in the y direction. A is going to be the vector, and I'm going to write them vertically because that's the way it shows up in the web work homework. So I'm going to have the vector 3, -1, and my vector B is going to be the vector 2, 2. Well, if I were to draw these, and again, I can draw them anywhere in space as long as I keep the same length and direction. So if I think about vector A here, this says 3 to the right and down 1. Why the down? Because I've got a negative sign. If I decided to put the head of that vector the tail of that vector right there, then to draw it, I would take 1, 2, 3 steps to the right and 1 step down. So I'm going to draw that here. That would be my vector A. So my y coordinate is negative, but not my x coordinate on that vector. So the y coordinate, like the y direction being negative, says take a step down, not a step up. Hopefully that answered the question in the chat. For this vector B, 2, 2, so if I pick a place for the tail of my vector, and this vector says move over 2 to the right and go up 2, and that's where I would draw the head of that vector. Things that we might be asked to do with these two vectors include adding the vectors together. Well, one of the phrases that comes up when we talk about adding vectors is that you add them head to tail. What that means is visually, if I were to take vector A and add to it vector B, then I'm going to think about picking up this vector B and I'm going to put it over here so that the head of vector A meets up with the tail of vector B. It's the same vector as long as it points in the same direction and has the same length. So I'm going to take this vector B and I'm going to pick it up and put it over here. And there's my vector B. So the final answer for what the vector A plus B is, well, if we break this down on the graph, I know that to give the answer to this vector, I need to know how far total did we move in the x direction and how far total did we move in the y direction. And on the graph, if I think about vector A, that moved 1, 2, 3 to the right. And then when we added that to vector B, we moved another 1, 2, which we could get by doing 3 plus 2. So we also talk about adding component-wise. So when we add two vectors, we're going to add their x components to get the new x component. And now we're going to deal with the y components. So for vector A, we went down 1. And then when we added that to vector B, we end up going up 2. So if I go down 1 and then up 2, there's a net change of a positive 1. So when we draw in the vector A plus B, and I'm going to scoot this A over a little bit, but when we draw in the vector A plus B, we draw it with the tail starting on the tail of A and the head ending at the head of B. So this new vector here is the vector A plus B. I said that vectors have a length or a magnitude and a direction. So let's talk about, well, what is the length of each of these vectors and how would we talk about the direction? I'm going to start with vector A. Notation-wise, our notation for the length of A, there are a couple of different ways that it gets written. And length and magnitude, those are going to be interchangeable terms. But if I'm finding the length of A, we often denote that with bars on either vertical bars on either side of A. You can think about that as an absolute value bar, but really it means the length of A. It should always be a positive number, which is why I think they use absolute value bars. Sometimes in physics, you'll also see a double set of bars instead of a single set. But in math, we usually just have one bar on either side. Well, if I think about that vector A, finding its length is really, this vector A is the hypotenuse of a right triangle that went down 1 and 3 to the right. So if I were finding the hypotenuse, I'm using Pythagorean theorem. So this would look like -1 squared plus 3 squared. And the length for A would be the square root of 10. If I did the same thing for vector B, this would look like the square root of our x component squared plus our y component squared. So that is the square root of 8. Good times. There are a couple of different ways that we can talk about the direction of a vector. Yeah, sure. So there are a couple of different ways that we can talk about the direction of a vector. And option 1 is to use trig. And to use trig to turn the direction into an angle. And then give that angle in sort of our standard form, thinking about horizontal being the x-axis and the angles growing as I go around the circle counterclockwise. So if I were looking at the vector b and looking at that 2, 2, and I'm doing this one because I can do the radians without a calculator. If that's the vector 2, 2, then the angle that it makes with the x-axis, if that side's 2 and that side's 2, then I would go ahead and use tangent to get the angle right there. So I know that for that angle theta, tangent of theta would look like 2 over 2, which would be equal to 1. So because this is a nice number, I would expect us to know what that angle is. And I would expect us to know that that's pi over 4. However, if this number were something messier, like it's going to be when I do A, we would just leave it as arctan or tan inverse of that number. So let's say I'm going to erase my length of a vector here. Oh, so there's a question about, let me finish this off for A, and then I'll go back to the question in the chat. So if I were finding an angle for A, and if I put it on a standard coordinate system and I put the tail at 0, 0, then this would come over 3 and down 1. So it would be right here. And I'd be looking for the angle that it makes with the x-axis. Now, because this angle is down below the x-axis, I would usually report this out as a negative angle, but you could also report this out as the positive angle that goes all the way around to the other side. Standard is to call it negative when it's down here below the axis, positive when it's up here above the axis, and just go with that. So I would say that the angle it makes with the x-axis, I know that this side is 1 and this side is 3. So if I think about tangent for this picture, tangent of theta would be 1 over 3. And I would report that angle out as negative tan inverse of 1/3. For U, and I'm going to say that this vector U is looks like it's about 3, 7. Well, one of the ways that we can talk about the direction of this vector is to think about that's obviously way more than a length of 1. In fact, let's just quickly find the length of that vector. Well, the length or magnitude of that vector would look like the square root of 3 squared plus 7 squared. That's 9 plus 49. So it's that square root of 58. Well, that's huge. And that's way more than a length of 1. But one of the ways that we can talk about the direction of that vector is to think about shrinking this vector so that it points in exactly the same direction, but it's like the teeny tiny version of it that only has a length of 1. And we're going to call that normalizing the vector or unitizing the vector. And the physicsy notation for this is actually that we put a hat on top of it. We don't usually do that in math because if you remember from chapter 7, in this textbook, we use the hat to mean that we're talking about an equilibrium, which doesn't even make sense with vectors. So this right here, we need a different notation for it. And this little unit vector, we write as u divided by the length of u. And this is another way that we're sometimes asked to report out the direction of the vector. This is a unit vector or a normalized vector. Now I want to be really careful here because I think the notation, I think the vocabulary is terrible. A normal vector without the ised is not the same thing. So it's important that we're talking about the normalized vector. And I guess I think about this as that ending of ised means we did something to it. And so a normal vector means something totally different, and a normalized vector means we shrunk it down so that it has a length of 1, but it points in the same direction. So if I wanted the normalized vector for u, this would look like I'm taking that vector 3, 7, but I'm dividing each term by the length or magnitude of the vector. By the way, notation-wise, WebWork is doing these vertical vectors. If you wanted to match this up to how Professor Chaudhuri was writing them last Wednesday, he was writing this as 3 divided by the square root of 58, comma 7 divided by the square root of 58. These are both completely fine, acceptable, regular ways that we use notation for vectors. And my v vector is 2, 3, -1. Well, if I were going to draw this, this just means that I took 2 steps in the x direction, 3 steps in the y direction, and went down 1 in the z direction. Nobody is going to make you draw that vector. I mean, not in a testing situation. No one's going to make you draw that vector. Not now and not in 17C. We need to be able to look at it and know that we're talking about an x, a y, and a z. But don't worry about trying to graph that. If I had a second vector, and because I'm running out of letters, let's go w. If I had this second vector w and it looked like 0, 1, 4, then those same ideas of how I would add vectors or even subtract vectors component-wise still hold, even though we've got 3 components instead of 2. So if I wanted to find v plus 3 times w, then algebra-wise, we're just going to do essentially this same thing to the x components, and then to the y components, and then to the z components. So if I take v plus 3w, that means take 1 copy of the x component of v plus 3 copies of the x component of w. Do the same thing for the y's. So I'd have 3 plus 3 times 1. And then I'd have -1 plus 3 times 4. Or 2, 10, 12 minus 11. Great. So that would be the resulting vector. Now we can also normalize this, meaning shrink it down till it has a length of 1. And we can also find its length or magnitude. If I went to find the magnitude of this new vector, v plus 3w, then finding the magnitude, it's kind of like we're taking Pythagorean theorem, but we're doing it with 3 components instead of with 2. So this would look like 2 squared plus 10 squared plus 11 squared. We can do this. So 11 squared, that's 121. 221, 225. Square root of 225. That feels like it ought to be a nice number. Is that a nice square root of something? Oh, yeah, I made a mistake, huh? 3 plus 3, fun fact, is not 10. Three plus 3 is in fact 6. Thank you. Ah, man, now I gotta go do math again. Okay, 121, 36 and 4, so that's 40. plus 121, that must make this 161. So there's my length of the vector. And if I needed to normalize it, oh, I missed an L. Normalize it. The ending is important. So if I normalize that vector, it is going to turn into 2, 6, 11. But each of them divided by that length or magnitude. Are these numbers gross? Yes. Were my numbers gross when I worked through the Weber homework? Absolutely.